запустил.
Заодно проверим скорость. Кстати, еще там, скорее всего, понадобится, но потом файл записать. YouTube сразу будет сохранять.
YouTube сохраняет все стримы, если он указывает. То есть можно стрим потом сохранить как видео.
Я просто в YouTube там ну ты видел эти настройки, я там ничего не трогал.
Да, я ну, это нормально.
Так, амоников не хватает.
Ты хочешь, чтобы хватало ему?
Конечно. Там же люди смотреть будут.
Вроде бы склон.
Ну, если можно, если есть время, можно еще заморочиться и подключить. Я все равно боку. Я просто сейчас в торопях хочу по-быстренькому сделать.
Давай потом займемся.
Ну, просто там обычно есть выход под наушники, как раз его можно... В принципе, у меня есть, кстати,
Не, пока не заморачивайтесь, я думаю,
серьезно?
Чуть больше времени.
Я просто не знаю, есть ли в Маке там... Погоди, в Маке...
Там есть...
Там 4-пиновый?
Там 4-пиновый. Для него нужно...
У меня есть переходник.
Ты его сейчас пишешь на камеру?
Он может и транслировать, и писать.
То есть он может два выхода.
В смысле, он сразу и зал записывает, и спикер записывает, и еще может транслировать, у него выход есть.
Окей, тогда хорошо.
Мы сделаем паузу.
Кто-нибудь может проверить стрим?
Слушай, это 9 скопов, где можно перевести на ваши странички в YouTube.
Конечно, это надежно не выглядит.
Стрим поднялся.
Отлично.
Что там, все круто? Как есть?
Да, что-то больше. Я хочу, что ты закроешь, да.
Так, окей.
А вот с этим ты будешь слушать звук, да? Мониторить его. Зачем это?
В смысле?
Это штука.
Он сразу будет
наушники.
Наушники и транслировать.
Ладно, скажешь.
А вместо вот этой странной карты. Сейчас настроим. Я бы поставил микрофон поближе.
Я просто пока не знаю, куда его поставить. Если...
Возьми и включи.
Ты уверен?
Ну,
Не, а может есть еще
там
столько?
не критично, мы поставим сюда.
Не, а есть типа такой столик еще?
Зачем?
Поставить оборудование, микрофон надо.
Нет, я микрофон поставим спикеру, собственно, знаете.
А у него это... Отлично. Да?
Тогда вообще тогда лучше будет.
Я наоборот, чтобы зал как раз записывал.
Тогда да.
Do we have 20 minutes to another guests? 20 minutes
for some other guests. We might.
Sure. Is that maybe then a good time to get something to eat?
Of course, I think Misha should have handled that.
I'm sorry, my English is sucks.
Миша сказал еду, не знаешь?
А? Нет,
Миша.
не знаю.
Окей,
Все уже. Я
Окей, а
А еще я сказал, что так. Перед всем креслом
Ну, еду-то надо заказать. Ага, окей, тогда. Food is on its way. О, боже мой, product placement.
This is not our sponsor. Или как его там? Давай развернем, что ли, тогда?
Еще на...
Не-не-не, только не к спикеру.
Нет, это нормально. Камеру он не
Сейчас,
попадает.
подними. Ну, подними его. Вот так.
Кто-нибудь может проверить звук на стриме? Я вроде как переключил источник и... Нет. Нет, он плохой.
Не-не, он просто берет звук, наверное, не от того устройства.
Да.
А ты тебе слушай. Давай камеру переключим. Это, конечно, будет сейчас немного не так.
Камеру переключить?
Ну да, поменяй местами.
Окей, не критично. Сейчас он переключится.
Там можно будет угол побольше.
Я сейчас пофикшу экспожу, а то он тут фиговничает.
Слушай, знаешь, как проверить? Там все. Можешь чуть-чуть поднять, чтобы было видно эту шкалу? Ага.
Нет, по-моему, все еще работает.
I'm sorry again. May you speak example to петличка?
Тут петличка.
Welcome.
Ну-ка. Again, please.
Welcome.
Помни.
Да, не тот вкус.
Thanks.
Спасибо большое.
Ну да, как-то так.
Или давай я тогда с петличкой побегу.
Я знаю, попробуй.
Это я хочу? Так, вот, у меня еще одна тоже есть сейчас.
Да, да,
И записывать, и сюда трансляцию. И он не распознал подкаст, да. Хорошо. И я вот такие штучки вот с лишь приобрел.
Я ожидаю, что...
Очень просто поеду, но, блин, переговорить на самом деле.
Я почему-то не понял.
Я тоже спалил, только, блин.
Но на самом деле проблема в том, что 4-пиновые треки очень сложно.
Если у меня есть USB, можно какие-то спать.
Ну, можно попробовать. Ладно, если она работает. А что тогда будет? А еда какая? Всем или кто-то заказывает? Я бы вкинулся просто. Или хотят, подскажите, где мне заказать?
Давай просто сделаем.
Можешь себе сам закачать.
Да, могу. Я просто не знаю, где я хотел...
Слушай, я чувствую, что давай закажу пиццу с ананасами.
Что я настолько сильно долбанул, шарахнул по той штуке. Зачем? За что?
Пицца с ананасами бессмысленная и беспощадная. В целом я не знаю, почему оно не хочет.
Окей.
Но знаешь что, у меня есть интересное предложение.
А еще он работает как звуковой аппарат. Еще он работает как звуковой.
А вот это очень полезно.
Написать надо будет сюда писать.
Найди мне видео.
Блин, это экстремально, ну лучше, я думаю, оставить.
Сейчас-то куда оно пишет? Мы не можем проверить, что оно не пишет там. Но обязательно будет выдавать онлайн, но все равно сигнал. То есть оно не такое умное.
Да я понимаю, я просто о том, что это слишком ответственно сейчас. Это офигенный кабель.
Это Type-Y?
Да.
Type-Y может не подойти у него.
В смысле, не шутил сейчас? Просто Игорь сейчас не шутил. Короче, прикол этого кабеля в том, что на нем могут одновременно сидеть два устройства. Я не знаю, как.
Type-Y.
Я даже не слышал.
Что? Кабели Type-Y?
Да, я вот сам сейчас
такая Type-Y. Ну, точнее, USB от AGY, но не суть.
Тогда это можно
заряжать и
Да.
Ну да. Но он на нем не могут данные себе устройства.
Могут. Можно в одну дырку подсунуть флешку, в другой дырку заряжать и
Заряжать. Но нельзя подключать.
Да.
Я кут подключал вместе с еще чем-то. Хит.
Но в целом удивительные кабели, в которые можно сразу два устройства подключать данные передавать, называются USB-хабы.
Посмотри, просто может там что перезапустить надо, чтобы он переинициировал устройство.
Не, он сам подхватывает.
Просто BS, возможно, старая. А, 22.
Все же работает.
Я тоже говорю, блин, уже запись.
А в чем проблема?
Ну, типа, мы теперь думаем подключить этот рекордер как звуковую карту.
Все, короче, работает.
Писать сюда.
Работает, не проблема.
Да, вы управлять. Ну все, да, он же не переключается.
Все, давай фиксируешься больше на видео. Там нормально все?
Да, запись идет, звук регулирован, память есть, батарейки есть. Так.
Все? We can start? Ага. On the first floor.
Хинита петличка.
Хинида петличка.
Так, и сколько? С этих две такие пары.
А если сигары,
надо растянуть удовольствие. На месяц была.
Нет, тут, увы, еще и СПЗ прошитая.
Что?
СПЗ, увы, прошитая, то есть никакой романтики с ламинатом.
Бездушная работа.
Пару вечеров.
Можно взглянуть оплату?
Неделю вводишь.
Неплохо, да. В принципе, как-то.
А где взять эту ссылку?
Такой чувак,
Где взять эту ссылку?
Кстати,
А, да не, вот там внизу.
Да.
Так что ты можешь не конкретно эти.
Тут у меня только что смотрели.
Нет. А вот на еще наклеить. Не открываешь наклеить. Почему можно воткнуть что-нибудь аналогичное? Ультрафиолетовый прям стирается на панель, отклеиваешь наклейку, ставишь туда. Он еще растет. Электричный, все.
Ух ты.
Так можно найти.
Камера? Не, микрофон. Да, даже пушка получается. Ух ты.
Ну, в смысле, вместо переброшивать, флешку.
Скиньте мне кто-то в личку ссылку на этот,
Она лежит в чате здесь. Так далеко.
Все.
Так, надо хлопнуть 3 раза.
Ты экранчиком поставь, чтобы видеть, что там реально что-то говорит. Подключи по этому.
на самом деле, в чем проблема с самого начала камеры?
А?
Камера не подключается в стриме, а вроде можно слушать.
А как на захват?
Нет, камера может быть как камера внешняя, обычная.
Надо HDMI захват.
Серьезно? Я думал, что он как вебка.
Она должна быть как вебка.
Я хотел себе зеркальную вебку. Думал, будет самый
Нет,
крутой район.
большинство вещей, которые могут записывать видео, могут стоять
Не может. Все,
А
начинаем.
тот у тебя штекер не до конца был.
Нет,
Да,
It's now or never.
там это звук сейчас обратно надо.
Дай мне зарядку.
не, ну, когда они тестят подушку, то есть вес на ты просто разводишь маточку, втыкаешь, можно.
Let me speak from my heart. Make a post on the Russian /dot analog, call it Hubbard.
Oh, cool. That's really great. So my name is Walter. Together with a friend of mine, I've built the Gigatron TTL computer. So it's nice to be talking about this system. It's nice to be here in this hackerspace. This is one of the neatest hackerspaces I have been to. Everything looks very tidy. And also, I've never been recorded by so many recording devices at one time. So I'm sure that people who watch this later will get a good recording. So this talk normally would take about an hour, but I can make it shorter or I can make it longer. Is there anything in particular you would like me to talk about?
I think there is no much technical specialist here, so if you focused on the fun stuff, it will be better.
Okay. So I will talk a little bit about how this system works, and I will become a bit technical. But I will also talk about the whole journey we made from thinking about making this into completing the design and making it into a kit. In a kit form. So it's really nice to be here in Russia. Of course, English is not your mother tongue. It is also not my mother tongue. So I hope you understand what I'm saying. If not, just shout out, and I will repeat stuff in different words. Right? Also, if you have any questions at any point in time, I'd rather have you interrupt me, and we can discuss a little bit. And maybe it is already in the presentation, but it's fine. If you have any questions, just shout it out. Good, so my name is Walter Belgers, and as you can see I'm quite old. I started soldering a long time ago, in 1978, and I've also started programming in 1978 on this computer. I actually have the same computer that I started on in 1978, an XD Sorcerer computer, and I like computers. I have a whole collection at home of old computers from some microsystems, but I had all kinds of computers. And I also like being in Russia because I know that in countries like Russia it was really hard in those days to get hold of a computer. And there were many more people that had to build something themselves or adapt existing computers, whereas where I'm from, you just bought it or got it or your father got one from work and that was it. But I think over here there's much more people really playing with computer systems. And this talk is about what we call Gigatron, a TTL computer, and this was the first version of it on a breadboard. And actually a friend of mine, Marcel, he started out with building this. There you see Marcel on the picture. And together we've built it into a kit. And the idea was, what if you start with very simple TTL chips, or over here you have the famous 155 series. If you have these simple chips that do almost nothing, like NAND or NOR, or maybe a multiplexer, or a combination of NORs and ANDs, what can you build out of those components? So if we now take a lot of stuff from the late 1970s, early 1980s, what could you build with that these days? And the idea was to build a home computer or a CPU, central processing unit, and there's actually a whole bunch of people on the internet doing this. And there's a home group CPU ring, and you will find many websites of people playing around with hardware, building a CPU. Right? So you can buy a CPU ready-made. So that's the famous MOS 6502 processor that you will find in the Apple I. This is an Apple I computer, also from the end of the 1970s, and you will find it in the Commodore 64. But this is quite a complex chip. There's the diagram of what's in there. So there's it can do arithmetic, and there's registers and stack pointers and program counters. But we wanted no CPU. We wanted just the TTL logic. So CPU. So we are going to build the microprocessor out of these very simple things. So the idea was we are using the 7400 series TTL logic. Why? Because they are very simple chips, but also because you can still buy them. They are quite old, but you can just still get them, and also the old versions with which you solder through a hole inside of a circuit board. So we did want
use it or brand new?
Brand new. Yeah, they are still being produced. We did not want any complex chips with a lot of stuff in there, so no CPU, but also no ALU. So that's the arithmetic unit, logic unit. So this can do calculations, and as you can see, this is quite a big chip. Also, I don't think they are produced. You will see that some people build their computer out of multiple boards, but we wanted just one board to keep it simple, and we wanted only to have maybe 30 or 40 chips on there. The idea was also to make an 8-bit system, just like the Apple or the Commodore. Have a bit of a retro look. It should look a bit old, but it's not very hard with those old components. And it needed to be somewhat useful. So in the beginning we thought we would have a few buttons and maybe a few LEDs, but during the design we found out we could do more with the chips, and we aimed for simple games. And maybe a clock application, because if you have such a neat box you don't want to store it in a cupboard, but you want to have it on display. So it must do something useful. So the idea was, if we have this thing make a clock on the screen, you can have it on all day. We also wanted it to be educational, so you can learn how computers work from building it and using it, and of course it should be fun. So those were the design goals. Simple system with just a few components. But the design goals are not set in stone. So if we come across a problem and we need to do something, well, we can tweak it a little bit. So we have, for instance, tweaked it a bit. We have included micro USB connector. So of course that's cheating, because in end of 1970s there was no USB. But we only use it to power the device. So that, for us, that's okay. It's only 4 or 5 volts. And we use a high-speed, low-power version of these chips that were not available in the 1970s. Now they are, and that means this whole system will use only a few hundred milliamps. But you can still put in the original chips from the 70s, and it will still work. It will use a lot more power, but if we build it for the kit, we use the newer version. We wanted to keep the hardware as simple as possible. And I will repeat that a couple of times during my talk. When you can solve something that we need to do with the computer in software, that's what we would do. Because it's easy to write something in software, and it's hard to change the hardware design. And actually this computer is super simple, and still it can do a lot because of all the software in there. And we started simple and just went with it and saw where we could get. Now a little bit of background about computers. So a computer, the green block, that's the central processing unit, the CPU, the microprocessor. But we don't have a microprocessor, we have to build this all ourselves. And in it is something that can do calculations. There is a control unit that determines what is going on in a computer, and there's some memory. Then we have internal memory, external memory like disks, floppies, hard drives, and we have some input and some output. Now, the external memory, disks and stuff, we said that's just too complicated. We're not going to use any, there's no SD card, maybe in the future, but now there's no SD card, there's no hard drive connected. That's too complicated. For the internal memory, we use 2 chips. The chip on the left is an EEPROM. It looks really old, it's nice. So this is a chip that you can erase by using UV light, and you can reprogram it. So that has the program in it, and we have a RAM chip. And now the first design question is, how do we run the program, and how do we get the program to do something with the RAM? And in the 1940s, the computers had the Harvard design, which is not used anymore actually. And in the 40s came a guy called John von Neumann, and he wrote a famous paper together with a few colleagues about his new design. And his new design meant that program and data is in the same memory location. And that is what, if you take your phone or your laptop, it all uses von Neumann. This means that you can put a program somewhere in memory and just start running it. Now that was revolutionary at the time, because before that you had, as I said, Harvard. And in Harvard you have program memory, stores the program, and you have data memory where you can put stuff in and read it out. But you cannot put a program in data memory. Actually, that's very secure, but it's really cumbersome. It's really hard to program. So that was an example of the first time that we had to make a decision. What are we going to do? Are we going to make a modern computer using von Neumann architecture that will be easy to program, but it is more complicated in hardware? So our goal was keep hardware as simple as possible. So we chose the Harvard architecture. So the hardware is really simple, but now programming is more of a problem. Right, so this is the same picture, but in a different way. We see again the control unit, arithmetic, I/O, program memory, data memory. we have these two chips doing that. And the program can, in our computer, only be stored in the EEPROM. Now, how does the computer run a program? Well, the program is a set of instructions, and it needs to read out the instructions and do something. Now, the instructions, of course, are in order, so there is a program counter pointing at where in the memory you are currently looking. You can step through the memory and run the program. So this is the board as it is here, and here you see all the components, and I will highlight them throughout my talk. So here, for instance, is the program counter. So we use 4 chips, and it's just a counter. And they count. It keeps track of where you are within the program. And this is needed. This is the clock circuit. This just increments the counter every clock tick. And here we have the ROM that contains the program to be run. There's only a few components. And then we have some more stuff, but it's only for the 5 volts, or the 5 volts that we need. So we have some protective circuitry in case you have a short circuit. So it runs on USB power. Right, so we have a program counter and the program ROM. And as I said, the program counter points somewhere in the ROM, and out come the instructions. So an instruction is just a byte. In our case, because we have an 8-bit computer, we have 8-bit instructions. So this thing means something. It is an instruction, and the question is, what do these instructions do? And this is really nice. If you build a computer with a microprocessor, the instructions are already in the microprocessor. So if you buy a 6502, you have the 6502 instructions. If you buy a Z80, you have the Z80 instructions. But since we are designing our systems, the system ourselves, it is up to us to decide what these instructions are doing. And here we have another design choice. There's 2 types of computers. There's computers that use RISC and use CISC. So with RISC, you have the reduced instruction set. You have only a few instructions, and they are very simple. So you need a lot of them to do something. And you have CISC, complex instruction set, and there the instructions do something very complicated. But that's really complicated in hardware, because a CISC instruction does a couple of things. Each instruction can do more things. So you give an instruction to the processor, and it needs to go through a loop and do several things. Well, that's way too complicated for us. We are just going to use RISC. So if we have one instruction, it does one simple thing, done. And that makes programming a bit more difficult, but we said, well, that's fine. Easy hardware, difficult to program, fine. Now you can have instructions that tell you to store something in memory or incremental counter, but you also want to give operands. So if you have an instruction to store something in memory, you also want to point where in memory you want to store it. That's the operand. Or if you want to add something, you want to tell the system how much to add, the operand. So, and we have decided that each instruction of 8 bits has one fixed operand of also 8 bits. So this might be the instruction, put something in memory, and this then points to where in memory that needs to happen. Sometimes the operand is not used at all. If I have an instruction that says you need to increment something with 1, and that's just the instruction, we don't need the operand, but to make hardware simple, in our program ROM, each instruction comes with one operand, always. And again, we cheated a little bit. We used an EEPROM that does not output 8 bits at a time, but 16 bits. So the first 8 is the instruction, and the last 8 is the operand. And that is being stored here. So each clock cycle, 16 bits come out, 8 bits are the instruction, and 8 bits are the operand.
And program counter is also 16 bits.
Yes. So let's dive into the instruction. So it was really cool.
May I ask a question?
Yes, of course.
Is the instructions with two instructions addressing two registers, data registers?
I will show you the instructions later, but it's all very limited. So you cannot say I have two registers and we also have very few registers. But I will go into it. So the cool thing about designing your own computer and your own processor is that we get to decide what happens with these instructions, as I said. And so the instruction is like the controller. It controls who has access to what kind of operation, what kind of arithmetic I'm doing, what happens to the program counter, what happens to registers. And it's up to us to decide what it's going to do. And in the end, this came out, and this is a piece of hardware, and in go the 8 bits of the instruction, and then some magic happens, and out come 19 signals that make sure that the right thing happens in the system. So we decided what kind of instructions it would be able to do, and we decided that we would use 2 bits to determine who has access to the bus. I'll explain in a minute. We reserved 3 bits for the address mode, and it's also used in jumps, and 3 bits for the actual instructions. Now let's have a look. So the bus access means we have things in here like RAM, ROM, input, output, and they need to talk to each other. You do that over the bus, but not everything can talk at the same time. So we need to control who can talk to each other. So 00 means the operand, which comes out of the program ROM, is sent to the bus. We can send the RAM to the bus. We can send the accumulator, which is a register, or the input to the bus. Then we have the instruction. So this is what it can do. It can store something, load. It can do an AND, an OR, XOR, an add, a subtract, store into memory, or it can do a jump. And that's everything there is. That's not much. If the instruction is one of these 6, then the middle 3 bits are the address mode, and they determine where we are going to store. Sorry, I'll show you. This is the arithmetic unit, the ALU. So this can do computations. It always does a computation with the accumulator and the bus. Nothing else is possible. So this is a register with a value, and this value can come from different sources. It does some sort of calculation, and then we have a result. Now it's interesting that traditionally, out of the ALU also comes a lot of status. So if you do an addition, you say, I want to add this with this, it will automatically tell you if it was a positive number, the outcome, or a negative number, or if it was 0, or if you have a carry. But for us that was too complicated. The only thing that comes out of here is a carry. So if you do an addition and it doesn't fit in 8 bits, you get a carry flag, and that's the only flag we have. If you want to know if the result was 0, you need to write some program code to check it out. If you do one of these calculations, then the middle 3 bits are the address mode, and they determine 2 things. They determine where the RAM pointer is pointing to, and where the result of the computation goes to. So let's make it clear using the example on the left. You see there 01010100, that's a valid instruction. So the first two bits, 01, they mean the RAM value goes to the bus. So we're going to take something from the RAM and put it here. Then these 3 bits mean, well, the RAM address we are going to read from is the location YD. So Y is also a register, and D is the operand. So this points to where we are going to read from the RAM. And we also determine that the result goes back into the accumulator. And the instruction was add, so we're going to tell the ALU to do an addition. So So it looks quite complicated, but with a few instructions we can now do calculations on memory addresses or on input and write it to the accumulator or write it into a register or to the output. And as you can see, we don't have many registers. We have X and Y and the accumulator.
And the RAM value accumulate with add with the accumulator.
Yes, the ALU always uses the accumulator together with something else.
Question.
Yeah.
So this current instruction is essentially take something from the address and add it to the accumulator, more or less.
Yeah, it takes something from the
Then
address.
nothing else comes
That's
out.
it.
It's just kind of like pick
It's a
something
data.
up, sum it. Yeah,
Yeah.
gotcha.
So we had something.
Yeah,
We take something from RAM, add it, put it back, done.
gotcha.
And how is different to the classic models usually used?
It is kind of the same as classic models, but this is very simple. So we only have a few operands and we have only very few registers. So with a normal CPU, you have many more registers. You can also use 16-bit registers, and we don't have any of it. So that means you need to do a lot more programming. So in a normal computer, you can store anything, any result in any register and do all kinds of operation between registers. But for us, you constantly have to move it to the accumulator, do stuff, and move it back. Yeah.
And for example, in ARM processor, in load instruction, ALU used to calculate an address. It can calculate some offset to address, but this is impossible with this process.
No. Well, you can use the registers to point to a certain value, as we do here. So the Y register is used here to determine where in the memory you're looking, but you cannot do any calculations on that.
Not in a single, not with
Not
a
in a
single
single,
instruction.
right.
Yeah, you can do it.
So here you see this decoder. So as I said, the instruction has 8 bits, and out come all these signals that do something, that tell the LU what to do and what to do, put on the bus. So that's the thing that controls the whole system. And that you can see here on the board, and actually you see these diodes, you can actually see that it is kind of a ROM. So if this signal is high, it does something there. And you can actually trace on the circuit board exactly how that works. And if you wanted to, you could change the instruction set just by changing these diodes. Actually, there's one guy who bought a Gigatrone of us, and he's really into chess computers. And he hasn't done it yet, but he wanted to change the instruction set to make it easier to play chess. So if you want to, you can. The last two I haven't talked about yet. So we have also a store instruction. So if you use the store instruction, the bus goes to the RAM. That's the only instruction we have to put something in the RAM. And we have a branch instruction, so that's a jump. And we have 8 types of jump, depending on the accumulator. And this is actually quite interesting, and I could talk 50 minutes about just how this works in hardware. Because as I said, we only have the caret flag, so we don't have a flag to see if it is 0, but we were still able, with some clever hacking, to make the hardware such that we could do this. So we have these kinds of jumps, and we also have a far jump that I may explain as well, but maybe not. Let's see. So that's the ALU, so that's the thing that does the arithmetic. So we have one of these chips per bit. 8 chips, 8 bits. Let's talk about output and input. So to control something, you can use out here, and then the accumulator goes to the output port, depending on what is connected to the output port. And for input, you can use input goes to the bus, and you can use many combinations of instructions to do something with the input. So let's talk about the input and output. The output was originally designed to be an LED matrix. So when the project started, we thought we can make something that plays a simple tic-tac-toe game on this thing. And then somebody had a YouTube video about the Quark 85, which is a very tiny microprocessor, 80 tiny. And this person was able to generate a VGA output using this 80 tiny. So this is actually sending the raw VGA signal to the screen, calculating it live. And then we thought, wow, so you can do with quite simple electronics, you can do VGA output. Couldn't we build VGA into the Gigatron? That would be much cooler than the LED matrix. And actually VGA is not as difficult as you might think. It's quite easy to do. At least if you take the simplest form of VGA, that's 640 times 480. And what you do is you just output the color bits, but you also need to send synchronization signals. So after every line on the screen, you have to send this horizontal sync pulse. So the monitor knows it needs to go to the second line. And after you've done a full screen, you need to send a vertical sync pulse, so the monitor knows that a new screen is starting. So that is what we needed to add to our computer. We need to send horizontal and vertical sync pulses to be able to make VGA signal. And the timing is quite critical. If you want to make VGA, the timing must be right. But we are using RISC architecture, right? So every instruction takes one clock tick. So we know exactly, it's very easy to calculate how long it takes to do a piece of program. So we decided to let the Gigatron run on 6.25 megahertz, which is a quarter of the speed of VGA. And that is also the fact why the X register in the system is a counter, because that makes it easy. So what we do is we take values from the RAM and we put them onto the screen. And the Gigatron is just fast enough to do that, and only that, at a quarter of the speed of VGA. So that just means that every 4 pixels, the pixel changes. So we have a quarter of the resolution. And that's also the reason why the X register is a counter, because we need to send the pixel to the screen and increment the counter. And if that would take 2 instructions, it would take 2 clock cycles. So we made the X register a counter, so we have an instruction that we can say the RAM needs to go to the screen and increment X. And then the next instruction, the next value goes to the screen, and we increment. Next.
I see you have a missed lines in your video.
Yeah, I'll explain.
Okay. Oh, and sorry, I'm not sure, I'm not familiar enough with video protocols, but as I know, the VGA is analog, and there's many digital.
Yeah, this is analog. This is the old VGA.
And protocols like HDMI need much more.
HDMI much too complicated.
Okay.
And this is a bit cheating, because VGA did not exist in the late 70s. But we thought, well, you know, this is.
Yeah, but it's very similar to TV protocol, because basically this is very close to Atari console 2600. You just missing TTL-chips, which need to like put colors, and that's it. Yeah, we didn't want a separate modulator thing in there. So we were quite happy with VGA. This is the simplest form of VGA. It's just analog, and the screen is like this. What you see on the actual monitor is just part of the whole screen. So you write the lines all the way to the back, but the last piece is not shown on your TV set. And also the last lines are not shown. Right? So you write the pixels, then you do the sync, and then you have some time. So that's time. In the old days, this was needed for analog monitors to send the beam to the next line. And then you do new pixels, and then you have a bit of time, new pixels, etc. at the end. And on here you set the vertical sync, and you also have some time in which nothing is displayed. So this time is needed to get the beam back.
Yeah, to get the beam back up to the first line. So on digital monitors, that's still in the, it's in the protocol, so it's still being used. So timing is very critical for VGA. If your timing is a bit off, the modern monitors will stop showing the picture. But timing is easy for us because we have RISC. Every instruction is one clock tick, but it's really hard to make a program, to program in machine language and to get all the timings right. So one of the first things was, this was solved by, in the very beginning, creating a software interpreter. So that's a piece of software in the ROM, and that will do all the writing to screen. So it will write pixels, and here it will send the horizontal sync, and it will look to see if there is anything else it needs to do. And you can put code in the ROM, and this interpreter will take the code and look, this instruction is taking 5 clock ticks, or this piece takes 5 clock ticks, we have time for that, let's do it. It gets back, oh, there's another instruction, also 5 clock ticks. Yeah, fits in, does it. Next instruction, oh, we don't have any time, I'm going to do the next scan line. So this is done in software, so there is a interpreter running that takes at every scan line a bit of the code that we have written to see if it can be executed. And with that, VGA was in hardware super simple. It's just sending out data out of the VGA plug, so we have a few resistors as a simple digital analog converter, and that goes to the screen with the H-sync and the V-sync. And that's nicely 8 bits, so that's good. So because the speed of the computer, we only change the pixel the color every 4 pixels. So horizontal, we only have 1/4 of the resolution. And vertical, we have a problem that a whole screen is bigger than the RAM. We have 32K of RAM, and it doesn't hold a complete screen. So what we do is we repeat the same line 4 times. So then we only need 1/4 of the RAM, and it fits. And then so then all the pixels are actually 4 times as big as normal. And so the resolution is 4 times as small horizontally and 4 times as small vertically. Effective resolution 160 by 120. And there's that line. To say, well, you know, if we repeat the same line 3 times instead of 4, then we have one line that we can keep black, and during that one line we have time to do actual stuff. Because otherwise we only have a little bit left for our real program, and the rest of the time is only VGA. But if we have this extra line, then we see we have more, we can do more computations. And in the later ROMs you can actually switch between 1, 2 or 3 of these lines. I'll take a break in a bit, but first this. So this was one of the first test pictures that we got out of there. So this is 160 by 120 VGA. And the hardware is only this. We have an output register to store the byte, and the 8 resistors, and a VGA plug. That's it. Now, can we do more output? We had this. We were already very happy that we could do VGA. But of course you want more. So can we do more without putting in much more hardware? Well, you know, we thought we have these sync pulses. So every scan line, there's a sync pulse, and during the sync pulse, we don't need any screen output. So could we maybe redirect the output to some other device? Maybe some. Sure. So during each horizontal sync pulse, that 1 byte doesn't go to the screen, but goes to 4 LEDs, and the speaker output. So we can change the status of the LEDs every scan line once, but that's fast enough. And we get this actually for free. We already had the hardware. So with the same hardware we can also do 4 blinking lights and audio. Well, we need 1 chip to store the stuff, and there is the output connectors.
Sorry.
Yeah.
But if we draw a picture, we will see. Here.
No. What happens is that if there is no pulse, the output goes to VGA, and when there is a pulse, the output is redirected not to the screen, but to the audio and the LEDs. And what happens is then during that pulse, it's stored in the chip, and then it's there until the next scan line. And we needed input because now we thought, now we have enough stuff in there to play games, so we want to play games.
Can I ask about video?
Yes.
Why you make it with software only rendering? Making hardware for this purpose, not difficult.
Special purpose hardware. Well, actually, this is mainly a VGA card with a bit of computing power in there. I don't know how else I could easily make it without using maybe a microprocessor, 80 tiny or something.
Okay, I just seen one guy make video card from two chips, one for store image, another for combination logic, and counter.
Yeah, but we want to have, but that's a static output, and we want to have dynamic output. So in those solutions you would end up with actually two processors, one doing the video part and one doing the computing part. And we have integrated it. We have built a thing that does mainly VGA card stuff, and in a small percentage of the time it can also do games. So the games, we wanted to have a simple controller. So we found the old Famicom controller, also known as the NES controller, and that normally has a really weird plug, but there's also versions that have a DB9 plug, which is much more easy to find. So we use that one. It does contain some electronics, so we had to reverse engineer the controller. And what happens is that you need to send it a pulse, and then to start pulling it, and then you send the second pulse, and every time you send a pulse, out comes one bit, one for each of the buttons. So I thought, oh no, we need more output because now we need to send signals to the controller to start reading out what buttons are pushed. Hey, wait a minute, we already have output with those H-sync and V-sync signals. Let's just take this wire from the V-sync and send it to the controller to start pulling. And take the wire from the horizontal sync and send it to the controller to start reading out the bits. And that works. So every time a new screen starts, it sends the signal to read out the controller, and then after every line, it reads one bit from one of the buttons. So in software, we need to make sure that we wait until 8 lines have been displayed, and then we can read out the contents of the controller. And the only thing we need for that is one chip to hold that input.
So in milliseconds, how much is delay, input delay?
Oh, not noticeable. So, what have we got? We have a CPU, and there is no ready-made microprocessor like the 6502. We build it all out of simple stuff. It's a RISC computer. Simple instructions. One instruction does one thing. It runs at 6.25 megahertz because of the VGA timing. We have 32K of RAM, which is needed to store a few images and games. We have VGA output, we have sound output, we have blinker lights, we have controller input, and we have this piece of software, the interpreter, that makes sure that we do not have to worry about the timing at all. And I want to go deeper into the software, but shall we first have a little break?
Yes. Можно попить чаю, туалет на первом этаже, ровно точно так же, как мы находимся.
Разделенные чипы, да? Нет, просто как
It's an actual picture from this.
No, it's an emulator.
Этот самый PS2 вот эти штуки, одна кофта надо. Нет, это тенька, да.
Я пробовал, кстати, на эмуляторе. I tried this game on the emulator, and it's very complicated. You need to stop every time.
Проще было бабахнуть на знакомые
Класс.
Ну ничего другого, никого другого. Один из первых отсканировал, отжать первых отсканировал картину, которую
Все, понял, я понял.
ну это типа там...
Она еще голая там. А, кстати говоря, есть фото, по-моему, как раз
можно получить каноническую
Мне кажется, что больше ты случайно не знаешь, что чей стол?
Нет, ну на самом деле вот по с вычислением при переходе луча игровой автомат всякие вот эти вот постпонги там первые на карте вот такие что-то, они примерно так работают.
Ребята, кто хочет пиццу, здесь есть пицца. Я знаю, вы ждали. Там.
Так, осторожненько. Я прям.
Голодные хакеры из Поволжья.
Вот. Я обедал на ужином.
Мне кажется, я что-то все не ел.
Пока вы
Типа заработал сегодня? А если бы
Я целый день спал.
Нет, тоже здесь еще там пишут, здесь это видно, кстати.
Я до 3 часов ночи играл в Skyrim.
Который раз?
Я периодически. Когда я смотрю на свой стимовский там счетчик часов, мне становится очень грустно. Но самое смешное, что чтобы мне в него играть, мне нужно на мой MacBook Pro установить винду, установить количество полос, установить Skyrim. Потом я в него башусь там 2 недели подряд без сна. Что я делаю? Сношу нафиг весь монтаж. На этом игра.
До следующего это делать, да. Ну и что же есть несколько таких игр, там нет героев, все такое. Оборотов есть еще. Побежал так скорее.
Это самое Vampire Bloodline. Да, очень хороший. Ну, я надеюсь.
Как бы, я надеюсь, да.
Ну, я очень боюсь, что выйдет Киберпанк.
И что смогут ли они достаточно смелыми быть, чтобы проставить популярно. Они не просут, будет потому что там особо был дичь.
Самый страшный, собственно, играть самая дичь. И вот
Как еще называется? Vampire the Masquerade — это сеть. Онлайн называется игру. Потому что еще есть Redemption. Ну, нам тоже такой типа распуснул, уже вокруг с автоматами бегают. Ничем там.
Но мне, кстати, нравилась первая часть, как себя Я думаю, что они солют Майнкрафт. Не то же самое, как в Fallout
Они как бы по фану делают. Могли себе позволить делать для всех. Сейчас нельзя так делать. Хочешь делать богато и красиво, то надо делать игру для всех.
Ну, это такой момент, что, например, вот в Fallout во втором был, если у тебя
ставишь, бегаешь полным идиотом качком, инсталируете нормальные диалоги, все как
Если
В целом, он здесь существует. Я думаю, ты его услышишь первым.
Кстати, возможно,
Он очень любит задавать вопросы.
понятно, да. Все-таки, чтобы RC вводить, нам надо было бы еще.
Так, а как дойти отсюда до...
Он еще ног.
Еще одну цепочку. Ну, как бы у свечей, по-моему, халявно. В этом режиме ты просто байтик фигачишь.
Клавиатуры
Массив. Нет, ну, когда вы проиграете на стол, потому что свечей, он компонентный. А композитный,
Там деньги вести можешь, значит, все остальное тоже можешь.
А походу есть клавиатуры.
Чтобы это могу зажимать сразу несколько клавиш.
Будет же
Нет, это неправильно.
видеосистему могли бы очень долго там.
Ну, это я буду делать дальше. Надо потом держать так, что разговор о полиции висит. Да.
Вчера чувак прилетел, ну, программа. Да, у тебя постоянно генерировать контент. Да, если, например, если лишнее нет, 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 я даже не знаю, что это.
Может, после.
Но учитывая, зачем компьютеры были сделаны, нет, это
можно было бы сделать
Короче, ты еще не знаешь,
сейчас перезагрузить, да, нам нужен следующий актив.
помогает организации.
Нет,
Ну, поскольку глубоко я
может даже контролировать.
Я не админов,
Таисию уже проиграли, Центре проиграли, в Таисию уже пытались. Что такое работает внешний.
Давайте прямо там. Давайте мы еще.
Где звука? Или есть звук?
А вот это пас.
Колоночки?
Нет.
С собой?
Можем поговорить с
А я ему уже писал, он сказал, что мы затрем эту тему тоже. Но я хотел вам показать тоже.
Без проблем. Ну давай в формате в общем.
Она без спайки, собирается на 2 часа.
И продается как кино.
Да, я сделал лендинг, сейчас выложил там. Нет, 66. Нет, 66 баксов, то есть 66 центов.
Я уверен. Красная лампа. Да, ну, вот такая позиция.
Ну, блин. Я когда говорил, как вы говорите,
Ну, видимо, мелкосерийно и оно
не знаю.
Кто хочет меньше, то можно воспринимать как лучшая игра.
Сейчас, да, сейчас немножко ситуация меняется.
Ребята, если вы чашки юзаете, там, закидайте их, ну, то есть сносите их на кухню для начала.
Короче,
Осталось в России.
Аналогии вообще даже
серьезно,
ты пропишешь, что ли? И потом он тебе говорил, что не можешь купить.
Нет, это моя.
Окей, я он еще семестр горячий. Он целый полгода или даже больше полгода уже нормально.
Ну, я просто не
Самое внешнее из дерева, коробочка. А еще лучше из дерева.
Эту историю я видел.
Я тоже
Олег, считается, Олег.
Причем самое важное, то, что Олег был одним из первых, кто взял и собирать, или как это называется. Короче говоря, вот зазвание там сказал, что вот. Хотя он сейчас сделал ровно то же самое, что он делал, как ну, сделал сейчас. Ну, смысле мы тогда делаем то самое, как сказать, вы выиграли, короче, в игру, там, он стукнул прикол, да? Я тоже был расшарить 800 человек.
Ну, я, короче, пока это поверхность, она не плоская. Того подобного решения делать, как его
Вообще не потому что тебе нужно тогда три плоскости минимум. Вот я типа рассчитываю, понятно. Нет, ну синус из чего? В смысле, он у тебя либо имеет одну длину и там ширину, либо у тебя еще где-то там куда надо.
Ну, я к тому, что не знаю.
Я думаю, что регулярно Стоп. Нет, я хотел напомнить, на TTL you must get this picture. Микрофон. А я не знаю, как петличка переводится. А я думал, он запомнился.
Водка, матрешка, петличка.
Да, я уже сегодня посмотрел на слово. Так. I'm sorry. Формонтаж, а теперь можно просто так. Вот, мы возвращаемся, мы продолжаем со второй части нашего Гигатрона.
How's everybody doing? Am I going too fast or
It's okay.
too technical?
Everything.
Yeah. I can go more technical, but maybe it's better for after the talk if people have questions. I have some extra slides. I would like to talk a little bit about the software, because the software is doing a lot. I would like to talk a little bit about how we made it into a kit and what you need to do so. And of course I can do some demonstrations.
May I ask a question about
Yes, of course.
hardware?
Yeah.
What is the power consumption from USB?
About 300 milliamps. Is that right? Yeah.
So you can run it from the battery the whole day.
Yeah. Although if you put in the original chips, it is about 1 amp.
You need to make a mobile version. This is the
No, you can.
Does it get toasted with original chips?
Does it get?
Toasty.
Toasty, yes, it gets toasty. I have thermal images, and you can see it gets really hot.
Even with modern chips or just the original?
No, well, modern versions of the original. No, they don't make them anymore, right? So no, those are original chips. We tried to build one with the oldest chips we could still find. And that really became hot. So the interpreter is really important because the interpreter does all the timing for the VGA signal. It emulates a virtual PC, so we write not in machine code for this computer, but we write in a language we have invented ourselves, which we call GCL, the Gigatronic command language. So in this language we have something we call vCPU instructions, virtual CPU instructions. And so the interpreter is running from the ROM. because we can only run software from ROM. And it reads the RAM to see if there are any virtual instructions, and it then interprets them and executes them. So now we can actually have program code, interpreted program code in the RAM. And that program code is actually 16-bit. So the interpreter understands 16-bit virtual code and translates it into the 8-bit code of the Gigatron. And that looks a bit like Sweet 16. That was a language designed by Steve Jobs on the Apple I, because the Apple I is also 8-bit, and he wanted to do 16-bit stuff, so he built Sweet 16. And that's a language, and you can program in it, and it will be emulated on an 8-bit Apple I. So the result of our work is that we have well, if you look at it from the software, we have a 16-bit machine with a Van Neumann architecture. But the hardware is actually 8-bit Harvard. So in the EEPROM, we have the main program, we have maybe an image, and we can have multiple applications written in this higher level language. And the main program will take the screen data and put it on the screen. That's what it's doing most of the time, reading RAM and just outputting it. But as you remember, these edges, we have time to do something else. So in that time, so what it will do is it will load a virtual CPU application into RAM and execute that. So this is the main video loop, and this application is now also in RAM, and it's being executed or emulated and executed by our interpreter. This was one of the first programs that we built, and you can see it's also scrolling. That's actually quite easy to do. The way the memory is built up, we have a pointer pointing to the beginning of each line. So by changing the pointer, it's really easy to do horizontal scrolls. Of course, we made that to make it easier to make games. And there's also people who have started building emulators. There's now, I believe, 3 different emulators. And it can completely emulate the system. This is one of the oldest ROMs. And here you can see it do the game that you've seen in real life. So it's still quite slow to build the screen.
Sorry.
Yeah.
Did you get the idea for startup chime from Temple or
Actually, Marcel built a startup chime. I don't know if it was inspired by something, but at that time we weren't really into looking in the audio capabilities. So we built just something that did something, and it stayed in there all of the time. So we built these games, and the performance is actually quite well, given the fact that most of the time it's doing VGA. So this was the first PCB that we made. It was about 1,500 hours of work for 2 people. And of that, about 30% is maybe in the design, and 70% is in making it into a kit, writing the software, and doing all of that. So sometimes people on the internet think, you can just build something on your breadboard and then you have a nice new computer. True, and it's really fun to do, build your own thing on a breadboard. But if you want to make it into a product and make a kit out of it, that requires a lot more work. But still, it's fun to do. So let's dive into the process of making it into a kit. So this was the first prototype PCB that we designed, and we spent quite a lot of work in that. It took about 10 weeks of development, also because we had no experience in building a PCB. And we wanted it to look really retro, so we have really thick tracks. And we wanted the layout to be nice, so you can really see how the computer is working. And we want to explain everything, so there's a lot of text, and also to make it easier to compile the kit and not make mistakes, like putting the chip the wrong way around. And the first PCB had only a few mistakes, and it worked. So that was really nice. Here it's showing the breadboard version of itself. So we made it into a kit, and that meant we needed to find a supplier for the wooden cases. We needed the PCBs to be built, score parts, but also write the manual. And we were lucky. I come from Eindhoven, and in Eindhoven there's also two guys I know quite well who run the crypto museum.nl or .com maybe. They collect crypto machines like Enigma, and they also have made an electronic kit version of the Enigma machine, and they've been selling it for years. And they said if you want to make it into a kit for people to build it themselves, you need to make sure that the manual is really well. So so it's easy for people to build, and they don't ask you a lot of questions about stuff that doesn't work. So we spent a lot of time beforehand putting everything that we could think about into the manual to prevent people from having trouble making it.
It's not usual for DIY projects to have a manual.
No. And it actually contains a chapter on how to insert the components and how to do soldering and how all the electronic components work. Maybe if you looked into it. Just to make it easier, and actually there have been people for whom this was the first time they soldered. And actually I would not recommend doing a thing as complicated as this for your first soldering project, but those people were actually able to do so. So that's quite nice. So the kit consists of the PCB, the chips, and a bag of components, controller, manual, and it takes about 3 to 4 hours to put together, soldering it. It costs about half of that putting it together, so that's something that actually is quite shocking how much time it takes to build these kits. Because these bags, there's plenty of components, so I need to pick them all up one by one, put them in the bag, put the chips one by one from the tubes onto the phone, and program all the ROMs and etc. etc. And of course you need a little bit of marketing, so we sent a kit to this is the 8-bit guy, to the 8-bit guy, and we said, well, let's give the 8-bit guy one of these kits, and I think he will enjoy it, although he's not somebody who likes to solder. He's really he likes to use old computers, 8-bit computers, and we thought he's going to tell us that he misses BASIC, because we know that this guy likes to program in BASIC. We don't have any BASIC. In fact, we don't have a keyboard. We cannot. There's no SD card. The stuff is in the EEPROM, and that's what you get. Of course, you can reprogram the EEPROM, but not everybody has an EEPROM eraser and programmer at home. And that's exactly what he said. He liked it very much, and but he missed the BASIC. We also sent it to Dave Jones from EEV blog. Now he's really a guy into soldering and less into computers. And it was really great because this guy is super enthusiastic and he really liked the PCB and design. But he said this PCB could be better because this PCB, there is electromagnetic radiation coming from it because it's a 2-layer PCB. And if you would do it better, you would make a 4-layer PCB and have a ground plane. And but we didn't do that. And we also had very little experience in this, but he did a series on this PCB. He got the original KiCad files from us, and he transformed it into a 4-layer board, and he also did measurements on the electromagnetic radiation coming from that one. So it was really interesting to see what he did. Oh, and what was also funny is he didn't look at the manual at all. He just took the PCB and the components, soldered them on and it worked. And that's really when, so first stage of building this is really fun because you're learning new things, you are figuring out how everything works, and you also are doing different things like making manual, making hardware, making software, making the kit. And then there's the hard work of filling all the bags, doing all the boring stuff. But then people start to buy it and they send you pictures of how they made it. And that's really cool. So if you have a project that you're building yourself and you think it might be interesting to make it into a kit, yeah, do so, because it's really rewarding if you get positive feedback. And I get to stand here to talk to you, so that's also nice. So you get a lot of stuff in return. But there was one thing that we got back, and that is that people said we would like to be able to do some programming on it. So we wanted to expand it. And one of the last things we did before we sent the first version, here you see also, by the way, that we have version 3 of the ROM. So currently we have version 4. There are a few games here. Those games were written by people who bought the Gigatrons and wrote games themselves. But the last item on the list is loader, and that was a bit of our escape. I thought in the future we need to be able to put something in there without reprogramming the EEPROM. And there's only one input that we have. This is the only input that we have. And this is very rudimentary. We can only send one bit and then pull it out per screen. How do we do it? Well, what the loader does is it takes these bytes from the controller and it sees them as programming code, puts it in RAM and then executes it. So we can use this to send, this would be hard to toggle in a program using the keys, but using the same port we can send code in. So for that you need an Arduino. So we made an Arduino hookup, so you can tell the Arduino to send the correct instructions into the port. It will be loaded into the RAM and executed. And that eventually turned into this prototype. So we took an 80-tiny microprocessor. So that's actually a thing that is more powerful than the whole Gigatron. And what it can do is it can use PS2 keyboard signals into these signals. PS2 is simple enough still. USB keyboards are too complicated. PS2 is still around. People can still get PS2 keyboards. This one. And so we made it for PS2. And this prototype has now become what we call plug face. So this is also a do-it-yourself soldering thingy, very tiny circuit board with the 80-tiny and the input and output, that's it. So this contains the software to do the translation, and you can hook it up. And now we have written BASIC. So that was a huge improvement. It was really a very good feeling, because when we started with this computer, we thought it might drive a 9x9 LED matrix. And now we have a system actually running BASIC. And that opens up a lot of possibilities. So this version is called Tiny Basic. It's an existing BASIC. And what we even hacked into it is that you can save a program into the 80-tiny. So if you type in the command save, well, there's only one way to get information to the controller, right? That's via H-sync and V-sync signals. So those are fixed. Well, if we change the timing of the horizontal sync by 1 bit, it's still okayish enough for most screens to not lose video, and that 1 bit can be captured by the processor and can store it into the 80-tiny's memory. And then we can give a special command, so the 80-tiny will type back the program into RAM.
On what speed it operates?
Sorry?
On what speed it operates? Like 60 beats per second?
No, it's not. I will show you in the demo later. It's quite slow, and also there's only limited space. So you can write a program of 30 lines maybe, and then it's full. And then people started to do other things like a RAM expansion. This is by a user of ours. He said, I like to double the RAM. Well, you can if you like. We have a breakout for the address line that you need. You see a wire there coming over. You can put in double of the RAM, and fine.
And all these changes are not open source, right?
These changes are all open source. We have a forum where everything is on. Actually, everything that you see here is open source except the contents of the manual and the keycode files or the Gerber files for the PC. And the reason is that we are still trying to get a little bit back for our 2 years of work. And in the end we will stop selling them and also make the purpose. But there are actually people who have made their own PCBs and or built on a breadboard. The schematics are online. And there was always the question: can we do more expansion? And that led to a RAM switching board. So this is a bit of an experimental status. We have a few PCBs made, and then we can translate it to SPI protocol. And with SPI you can attach all kinds of hardware. It also acts as a RAM expansion. So what you do is you take out the existing RAM, plug this in, and you can put in the original RAM or a bigger one, and you get the extra SPI outputs to hook up whatever you like. So in this example, is this a movie? Yeah. We write some assembler code there to output 2 LEDs. And what you see here is an SD card, SPI SD card reader. And Marcel is the software guy. He is currently programming something that will be able to read SD cards. But that would also be a nice addition. And people have gotten all kinds of ideas. So there's one user who tried to overclock it. Of course, if you overclock it, because the clock frequency is for VGA, then your VGA doesn't work. So you can overclock to 8 megahertz, but then you don't have VGA signal. The system will work, but you have no output. But this guy overclocked it exactly twice, and then you have to make small software changes, but then you can get a working system. That's about the fastest you can get without, well, I think 15 megahertz is about the limit. But then you need the fast version of these TTL chips, the F series. There's somebody who made a very tiny version. Then there were people working on software, so somebody thought, let's have a C compiler. And they wrote a C cross compiler, but this is actually also a work in progress. There is a simple library, but you don't have many functions, so it's not like you can now easily cross compile C programs and have them run. But it's a start. But the latest edition maybe makes this obsolete, and that's that there is now a complete 6502 emulator in the Gigatrон. So instead of running vCPU code, the interpreter can run 6502 code. It is a bit different from an Apple I. Oh, it says here, I should say for Apple I, it is like an Apple I because Apple I has a 6502. So you can like run Apple I code, although it's on a different place. Memory and the I/O differs a little bit, but with minor tweaks we can run native Apple I code on the Gigatrон. That's cool because our idea was to build a computer system with simple logic that could have existed in the time of the Apple I. So we can run Wozmon. Wozmon is the hardware monitor written by Steve Возняк, and that was included in the original Apple I. So we can run that. We could already run that. It's in the EEPROM, but that's a rewritten version in our machine language of the CPU code. And this is native 6502 code. You can also run microchess, which is running here. Yeah, so that's microchess. It's very rudimentary because it's 70 stuff, but it's running 6502 code. I can't even remember what the slide is about, so let's see what's happening. Right. So here we are running the Wozmon, the Apple, what's it called? Disassembler to disassemble itself. So this is a famous disassembler for which Steve Возняк wrote a paper in the 70s. It's less than 500 bytes long, and it's a complete disassembler. So it's really cool that with this user community, really gets the whole thing going. And people are writing software. We are trying to improve stuff, but we have this community. We build a forum. People are posting on there, doing incredible stuff. So that's very nice to see. So let's have a quick demo of the system itself. So I have a cheap VGA to HDMI adapter, and it does actually seem to work. So I can use the adapter, the controller, to play games. Yep. Let's go back. So for instance, if you play Racer, you see the speed of the program, but I can also change the amount of black lines. So now only this part of the screen is used to do the game, and if you play the game now, it goes like this. But if I turn on one scan line, it's actually playable and I can do more and more. Of course I had to show in Moscow. So this actually has a nice audio with it as well. And I can plug in the plug face adapter. So I can run basic. And I can say save. Now we're going to see the display flicker maybe. It actually loses sync now. Now it's back, so now it has saved the program. And I can load it again.
List it again. Maybe it's...
what's the command? And so long ago I loaded a program. Where's the manual? Sorry?
That saving process, that goes from your control microcontroller?
Yes. Oh no, it is.
They can save only one payload.
Control F1. No. Control F3. Oh, that's it. Okay, so. Save. It's not a basic command because it's not a command that I type to the Gigatron, but it's a special key combination that the adapter sees and knows that it needs to output the program.
They can save only one payload.
You can only save one payload, yeah. So it is quite limited. If you want to do more, you could use the Arduino hookup and you can put in a lot of stuff. I also have an emulator with some other programs that you could put into the ROM. Where do I have the emulator? So this is just like the real thing, but I can drop, no, too far. I can drop programs into it.
Whoa, drag and drop.
This was also made by somebody other than us. This is one of the latest editions.
Call it a dinosaur.
Paint program.
Have you heard about taskboard on goodgames.quick?
Which one?
About taskboard.
Taskboard?
Taskboard. Tool assisted speaker on board. Why I'm speaking about it, it actually uses joysticks for executable, for injecting executable code into ROM of gaming consoles, and that is quite fun to watch. And it is really very reminiscent of what you are doing.
It's pretty old school.
The broader.
Yeah. Yeah, so this is the 6502 emulator. So this is the one I showed you before. I can do jump to 400. Do a disassembler. See, it's not really that fast, but still it's faster than the original Apple one. And some audio. But why is it so slow?
Less guidelines.
Yeah, but I don't get. Oh, it's this screen, I think. I'll run it on my other screen.
Just unplug HDMI and try running. Oh.
So this is what the screen resolution, right?
Too slow screen.
All these programs are in GitHub.
Oh, okay.
So we have a GitHub repository. There's also the emulators. You can also find them online. This is all open source. So if you'd like more, to see more, there's the forum. And here's another talk I did with a little bit more technical background. Спасибо большое.
Thank you. People from online translation, online stream asked to
translation people.
stream, not translation.
I'll be here for a while, so if you have any questions,
One question.
but it's not exactly this day. So maybe I'll